Now let us discuss about the combination of dielectrics in parallel. Suppose we have two plates, let's say A and B. In between these two plates, we have placed two dielectrics like this. Let's say a dielectric of dielectric constant K1 and another dielectric of dielectric constant K2. I am saying this as parallel because let's say here it is positive charge, the plate A is positively charged and the plate B is negatively charged. So the electric field in between these two dielectrics is the same because they both are between the plates A and B. Also the distance is D. We know the potential V is equal to electric field times T. The distance D remains the same. Also the electric field E remains the same. So that they are in same potential. Now we have, let's say, we have for parallel combination C effective will be C1 plus C2. We already derived this expression. If you have any doubt, you can always go back and check the video of the combination of capacitors in parallel. That is C effective is equal to, here C1 will be, C1 is equal to, see the dielectric constant of first capacitor is K1. So K1 epsilon 0. See, these areas are different. Clear? For the capacitance 1, let's take its cross-section area A1 and here the area will be A2. See, dielectric will be like this. It's almost like a block. Sorry. This is K1 and this is K2. So this is the cross-section area A1. This is the cross-section area A2. They both are different. Clear? Therefore, let me erase this. So C1 equal to K1 epsilon 0 A1 by C. There is no difference in the thickness. Both these dielectric have same thickness D. Similarly, C2 will be K2 epsilon 0 A2 divided by D. If I substitute these values in here, it will be K1 epsilon 0 A1 by D plus K2 epsilon 0 A2 divided by D. So this will be C effective. You can write this as epsilon 0 D is common. Epsilon 0 by D is common times K1 A1 plus K2 A2. Let's call this as equation number 1. Now, if I replace this with a single dielectric, let's say K effective, the dielectric constant K effective of the combination, and the let's say cross section area will be, it will be, let's take A, such that A will be A1 plus A2. Clear? If you add these two areas, that will be area of this plate or area of the cross section of this dielectric. And the thickness, as usual, it is remains the same. Thickness will be D. So that C effective will be, you can write this as K effective for this capacity, K effective epsilon 0 A divided by D. Let's call this as equation number 2. Equation 1 is equal to 2. Both gives the value of C effective. Therefore, we have K effective into epsilon 0 A divided by D is equal to epsilon 0 divided by D K1 A1 plus K2 A2. You can cancel this epsilon 0. Also, this d will get cancelled. So k effective is equal to k1 a1 plus k2 a2 divided by taking this a to the right, it will be a. But a is equal to a1 plus a2. Let's consider this also as the equation. We have k effective also a equal to a1 plus a2. So it will be k1 a1 plus k2 a2 divided by a1 plus a2. Okay. Now we have a special case, case 1, when a1 is equal to a2 is equal to half the area of the uh, effective, or what I'm saying is, I'm filling this dielectric in such a way that it occupies half the area of the capacitor, plates of the capacitor. So in that case, we have, that is like this, the dielectric is equally filled. This is K1, this is K2. In this case, both the areas are same and it is half the area of the plate. In that case, K effective will be K1. Instead of A1, you can write A by 2 plus K2 A by 2 divided by, you can take this equation A. So that K effective is equal to, you can take the A outside, it will be K1 by 2 plus K2 by 2 by A. Cancel this A and A. So that K effective will be K1 plus K2 divided by 2. Clear? So that's the special case.